Moving and manipulating objects are one of the most common tasks in robotics, and we tend to use robot arms to do this. But how do we control robotic arms? One of the ways we can do this is with ROS2 control, which comes with some advantages like being able to swap out pre-built controllers depending on what we want to do, or swapping out system components to control different robot arms. Meaning with one controller you can control multiple robot arms just by configuring it differently. We have previously looked at ROS2 control on this channel, links at the top and in the description, to control a mobile differential robot base. This will be different because instead we're controlling a robot arm which has different joints along the arm that we'll need to control individually. So we'll use an example from ROS2 controllers to show how to do that by running a simulation, taking a look at the code, and then pointing out the parts in the code that we need to change to make this work for a real robot arm. But before we get into any of that, let's dive a bit deeper into why we would want to use ROS2 control to begin with. So why use ROS2 control? What we're essentially trying to do here is tell a robot arm the positions of the motors that need to be put into place so that it can reach an object or manipulate it. Isn't that something that we can just write to the robot directly? Yes, there's some advantages that come with ROS2 control though. As I talked about in my JetBot videos on ROS2 control, we're splitting up the software to make it more abstract, so different parts of the software can be reused for different applications. In this case, we want to use a joint trajectory controller, which is essentially a path through space that you want the arm to trace, or to be more specific, that you want the tool of the arm to trace. So if you want to pick up an object, then you want to tell the arm how to get to the object in order to pick it up. And that path that we're tracing from where it is to where it needs to be is the trajectory. By using ROS2 control, we're splitting up the system, which defines how to communicate with the arm, from the controller, which defines how to move along the path. So the controller communicates with the system in order to move the arm. This gives us advantages like being able to swap out the system to go to a different robot arm, or swap out the controller to change how we want to control the robot arm. Instead of just giving a trajectory, we could give it to a PID controller that uses feedback to more accurately position the arm. And all we'd need to do to swap that out is to take our predefined trajectory controller and remove it, and put in our predefined PID controller. And all we need to do that is change our configuration file. So that's why we want to use ROS2 control. Not just for robot arms, but for robots of all kinds. It means that we can reuse our controllers between robots, and it means that for a particular robot, we can change how we control it. So with that in mind, let's take a look at the example repository and see how we can send a trajectory to a robot arm and see it move in space. This is the ROS2 control demos repository, which has a number of examples as we can see on the screen here. Now, if we scroll down to the README, you can see a list of all the examples that are available and what they deal with. The one we're interested in is example 7, 6 degrees of freedom robot. It says a full tutorial for a 6 DOF robot for intermediate ROS2 users. Now, by 6 DOF robot here, we're talking about a robot with 6 motors. That is, there are 6 limbs that can be moved separately, so 6 degrees of freedom. Degrees of freedom are more complex than that. But for a robot arm, it's as simple as that. 6 motors, 6 degrees. So if we open this example and then scroll to the README, it's got a little bit of a description here because there's more of a description if we follow this control.ros.org link, which has a full tutorial with a 6 DOF robot. You can see that there's quite a lot of detail on this page. One of the great things to look at on this page is how to set up the URDF, which I won't be dealing with. I'm focused on the code and how ROS2 control code works, but if you want to have an idea of how to build a URDF file and adapt one, this page is great at explaining it. So take a look at this. So links for the repository and for this page will be in the description. What we're going to do is check out the repository and run the simulation in my Ubuntu virtual machine so that we can see it running. And then by checking out the code, we'll be able to take a deeper look at it. So let's open up that Ubuntu virtual machine and start to clone the code. Here I am in my Ubuntu virtual machine. I have my terminal open and ROS2 is already installed. So if you're wondering how to do that, check the link in the description. you'll be able to work through that, and it's also available in some of the other videos I've made, but I'll skip over that. That's not the focus of this video. However, what we can do is clone the code. So what I've done, I've already set up a workspace here, but if we set up from scratch, I'll set up a new workspace, WS2, so that we can see how it works. So I'm going to make the directory, and we'll need a source directory inside that. So you can shortcut that with one single command. This makedid-p will create all the folders down the structure that you need. And then within that directory, we can clone the code that we were just looking at. So we'll return to the GitHub page, grab the HTTPS link, and then clone it inside this folder. With the clone complete, we need to make sure that all of our dependencies are installed. And there's one command that will do it, which is this rosdep command. The commands for this are both in the tutorial that I've already spoken about and in my blog post, which is the written version of this video. So feel free to check either to get the commands to set up this workspace. But we can use rosdep to install commands, or rosdep's installed successfully. This is good practice for any repository. There may not even be dependencies that we had to install here. Then we can go back up to WS2, and we can make sure that our ROS installation is sourced by doing source opt ROS Jazzy, if you're using Jazzy as I am, and setup.bash. And finally, we can run the build command, which is colcon build with optionally using symlink install. This is only really useful if you have Python in the repository, but it doesn't hurt if you don't have Python, so you might as well include it. Now, I'm going to cancel this because I've already built the workspace into my WS folder, so I'm going to switch to that folder. And remember to source the overlay workspace, which is done by source install setup.bash. Now we're able to run the simulation, and the commands are in the tutorial or in my blog post. The first command is to launch the robot controller, so this is the actual ROS2 control part. It also includes rviz, so that we can see a visualization of our robot arm while it's in motion. So here we can see the simulation, we can see the robot arm. There's another launch file that you can run, which gives you the joints, and you can actually move your robot joints individually and see how the arm moves. But for this, we want to see the robot move its tool in a circle, and a helper script is provided for this, which is from the same package, send trajectory. Now, I've altered mine. The original will run once and then sit waiting forever for you to kill it. I've edited it so that it will run once and then exit automatically. So you may see some difference in behavior. So you can see here that by running send trajectory, it's moving the tool in a circle. So let's see it again. Now you may find that it doesn't immediately respond every single time you send the trajectory. I'm not entirely sure why that is. So if it doesn't respond, if the arm doesn't move, just keep trying to send that trajectory until it responds. So we can see the robot arm again doing a circle. So there we have the simulated robot arm. We've seen it move by running a command. So let's dig into the code and take a look at how it works. Within the ROS2 control demos repository, there's this folder, example 7, which contains all of the code that's relevant to our example right now. So we'll skim over a lot of these files because they're useful as supporting files, but not necessary to understand how the controller works. First, cmake lists and package.xml just define the source code and how to build the library and what's available within it as a ROS2 package. The README has a link to the documentation and a small amount of information. And this XML file defines that we are building a library containing the robot system and the robot controller that we'll see later on. Next is the bring up folder, which contains a configuration file. And we'll look at this in more detail when we're reading through the controller code. And 2 launch files, which we've already seen launch the simulation and send a command to the robot to move in a circle. The controller we'll look at in more detail. The description contains the URDF file for the robot, which defines how long the lengths are of each of the segments of the robot and how they relate to each other, so the joints that join them together. Doc contains the documentation for this example. Hardware, again, we'll look at in more detail. Reference generator is out of scope for this tutorial, but essentially what it does is for a circle movement of the tool, it defines how to generate the joint angles that move the robot in that circle. So if you want to have a look at how the joint angles are generated, which we do need external software to do for our controller, you can take a look at this file and see if you understand it. The basics are, it can read the robot description file, the URDF file, and from that, it can calculate with inverse kinematics the joint angles required. Finally, the test folder, which just contains some test code that don't help us understand the controller, so we'll skim over that. So let's take a closer look at the controller folder, which contains two main files. The header file, robot controller HPP or R6 bot, and robot controller CPP, which are the header file and the source file. That's pretty standard for C++. This file defines the public interface, so what other software sees when it tries to interface with this library. So we can see that it's defined a robot controller class, which extends from the controller interface. So for all of these methods, if they state that they are overriding, that means they're overriding a method in controller interface. These three first methods are mandatory for a controller interface, and these four are optional. They're lifecycle methods, which means that they're called automatically by ROS2control at some point in the controller's lifecycle. OnInit is the very first to be called, for example. There are also variables that are used by the class during its runtime, so we'll take a look at those in the source file. Taking a look inside here, we're starting with OnInit. What this does is it reads out the joint names, the command interface types, and the state interface types. And these are defined by the config file. So if we take a look at the config file now, we can see that under the robot controller ROS parameters, it defines the type, it defines a list of joint names, it defines the position and velocity are command interfaces, and position and velocity are state interfaces. So from this, we can understand that the robot controller doesn't expect there to be 6 joints. It reads out as many joints as it's given, and it treats them all the same. It just expects that if it receives a message with joint angles, that message has the same number of joint angles as it is defined for. So if it has 3 joints, then all the messages it receives should contain 3 joint angles. For the command interfaces, not all robots support both position and velocity as commands. It may only support moving to a particular position, at which point the configuration file will reflect that. And the same with the state interface. For our simulated robot, it supports position and velocity both for command and state, so we keep those in. So that's what it's reading out. It's reading from parameters. Those can be defined in any way, but they have to be set as ROS parameters for the controller to function, or it won't know what to move. Finally, it sets up pointInterp, which is the current point it is moving the arm to, and all it does is fill it with zeros. Moving on to the next function, it's setting up the command interfaces. And all it really does here is there are 6 joints, there's 2 command interfaces, position and velocity, so it generates a string for every combination. 0.0 position, 0.0 velocity, 0.1 position, 0.1 velocity, and so on. And then it does exactly the same for the state interfaces. And it's pushing them into this interface configuration conf object. And what that does is it requests hardware interfaces at runtime. So it says, I need this interface in order to function, you need to give it to me, and then ROS2control is responsible for saying, that interface is available, here you go. Or that interface is not available, you will have to wait. So we've stated which interfaces that we want based on our joint names and our command interface types and state interface types. Then we can move on to the onConfigure lifecycle stage. What this does is it registers a callback. It says whenever I receive a joint trajectory message, which is the path that the arm will take, represented as a series of joint angles that the arm needs to be in to flow through that path. Once I get that, I will save the data and I will set a flag saying that there is a new message to follow. Now, one interesting note here is that it's using write from non-RT. And that's because ROS2 is not real time, it's asynchronous, but ROS2control is real time. It is not just real time, it's synchronous. So because we're moving across thread boundaries, we need to be a bit more careful with how the data is handled. In this case, we've received it in a thread callback somewhere, so we're going to write the data from non-RT, non-real time, meaning we'll do it in a thread safe way so that in our main loop we can access it. Then we go on to onActivate. This method is pretty simple. It is called when the interface reserving is done. So at this point, the controller has access to all the interfaces it's requested. So it clears everything, and then it saves the interface names to a map so that it can access them later, and that's all it does. Now we'll skip over interpolate point and trajectory point and come back to those and go on to update. Now this is the function that is called 10 times a second by ROS2 control in order to carry out any work for controlling the robot, for controlling the hardware interfaces that are being used. So in update, it receives the time and the duration. And what the update method does is it checks that new message flag. Do I have a new trajectory to follow? If so, I'm going to read it. And because we're in the update, we're in real time. So we're going to read from real time. We read out the data into our trajectory message. We save the start time, which is an important step. And then we set our new message flag to false, meaning if another message comes in, we'll be able to see that a new message has come in. Then it goes on, whether or not this function has triggered, it may already be following a trajectory. That's because we move to a point along the trajectory, and then we leave the update loop and wait until it's called again to decide where to go next. So we may be following a path already if we're at this point in the function. We call the interpolate trajectory point with our current trajectory message. And then we set all of them in our joint position command interfaces, and we set our velocities as well. This iterates over all of our position command interfaces and sets a value, and all the velocity command interfaces and sets a value. So this is the stage where it actually tells the systems controlling the robot arm, move to this point. One thing to notice here is that we are only writing data, we don't read data. So there's no feedback loop in this. It's a simpler controller. It's open loop, it says move to a point, and it expects the robot to move to that point and doesn't check whether it was successful. With that, let's take a closer look at this interpolate trajectory point, because it's useful to understand, but not crucial for how the controller works. So essentially what this does is it takes the current trajectory it's moving to, which is a series of joint angles it's moving between. It takes the current time passed in the update function minus the start time that it started following the new trajectory. So the time since it started moving along the trajectory, and it takes the current point that it wants to move to. Then it uses the current time, which is the time since it started moving, to figure out how far along the trajectory it ought to be. It figures out the last position it should have gone to and the next position it should be going to. And then it figures out the point in between them using the interpolate point function. All this does is figure out how far between the 2 points it should be. So if it's halfway between point 1 and 2, it should be 1.5. What this does is it allows the robot arm to move smoothly through a trajectory even when there's not too many points in the trajectory. It figures out a path on its own. That's the end of the update function. Again, we can see if there's a new message, it saves it and the start time. It figures out how far along the message it is, and it writes those position and velocity commands out, and then it returns OK. And that update function will be repeatedly called until it's finished going through the whole trajectory. Finally, the last method is the onDeactivate, and all it does is release its interfaces, which is a method from the base class. It says, hey, I'm done with these interfaces now. I'm closing down so I don't need them anymore. I'm releasing them so something else can use them. And then the very final thing is that it exports it as the controller interface so that it can be used by ROS2 control. And that's the controller. It is a joint trajectory controller and a slightly simpler one than the one that is available from the ROS2 controllers library. This is the actual ROS2 controller joint trajectory controller, which is available from ROS2 controllers. So because ROS2 control lets us reuse an existing controller, this controller already exists for moving a robot with a particular number of joints along a trajectory. So we didn't need to write the controller that's in example 7. We could have just used this controller. It would take exactly the same inputs and exactly the same information in order to work. So our example teaches us how this controller works, but for a real robot, we wouldn't use our controller. We would simply reuse this controller, assuming it meets our needs. The link for this will be in the description, and you can also take a look at the other controllers that are available for manipulators and other robots. For example, this PID controller you could use at the same time, except that it would actually read the robot's position and use it to more accurately position the robot arm. Next, we'll take a look at hardware, and this is the robot system. So again, a header file and a source file, and we'll take a look at these. And this is a very simple class. It declares that it is a system interface. And if you remember from JetBot, there's different hardware interfaces available. One is system, meaning it can read and write. One is sensor, meaning it's reading data only. And one is actuator, meaning it's writing data only. In this case, we're saying that we're writing commands and we're reading data back. So this is a system interface. Again, override means that we're overriding something from the base class. We're overriding the onInit and onConfigure functions and the read and write. So let's take a look at the source file for how this works. OnInit is very simple. It calls the base classes onInit. If it wasn't successful, returns an error, otherwise returns success. So it's only if something goes wrong in the base class that this returns an error. Then it does onConfigure. And what this does is for the joint state interfaces, joint command interfaces, and sensor state interfaces, it sets the state. So it says, hey, I made these interfaces available, so I'm going to set their initial state to 0. Now, one interesting thing is that we never see this variable being used again, and I'll explain why when we get to the next methods. So we'll skip read because write is very simple to explain. All that write does is says, okay. And that's because when it's told to write some information to a robot arm, no robot arm exists to write to. This is all simulated. So all it does is say, okay, I've successfully written the command. And then that helps us understand what is happening in the read function. Again, there's no robot arm to read from. So what read does is iterate over all of the joints, for each one generating the name of the velocity and the position interfaces. Then it will read the command for the velocity interface and set it back to the velocity interface. So this says, get the position, or rather, get the velocity I should be moving at, and then claim I am moving at that velocity. It is just echoing the velocity data back. The next is similar, but with a slight difference. It's showing us that we can start to calculate parameters about the robot, even in this simulated example. So it is getting the previous state, and it is adding on the current velocity that it's just set here, multiplied by the period.seconds. And this is a floating point. It means the time since this last was called, which is passed into this read function here. So what it says is, from here, if I'm moving this fast for 0.1 seconds, then I would have moved this far, which means my new position is that far along. Now, what we can do is copy. So instead of calculating our position, we simply retrieve the position that we've been told to be in. And the only reason that we've done it this way is in the example, it gives you an idea of what you can calculate. We're doing an integration instead of just reading the command back. And that's it for the hardware. The hardware is a simpler class to understand than the controller. And this is where we can start to understand the changes that we need to make for a real physical robot. First, the controller we can just delete because a joint trajectory controller already exists that we can reuse exactly as we need. So we don't need this folder at all when we're running for a real robot. The next is the description. Our description won't match our real robot, so we need to change the files in here to match our real robot. And finally, our hardware. We actually need to read and write from and to a real robot. So instead of echoing back the velocity, calculating the velocity as exactly where we ought to be, real robots aren't that perfect. They're not going to be moving at the speed they're meant to immediately. They're not moving to the position they're meant to immediately. So we need to actually read that data back out of the robot. And we need to write the commands to a robot. So those are the three things: delete the controller, change the robot description, and write the system so that it communicates with a real robot arm. And writing the system for a real robot arm is exactly what we'll be doing in a future video. We've seen that the purpose of the example from the ROS2 controller's examples library is to understand how ROS2 control can be used to control a robot arm. We used it to control a simulated robot arm, and we've seen that it defines a controller and a system. The controller being a simplified version of the joint trajectory controller, and the system being about as simple as it could get. It just echoed back the command values to the state so that the controller believes the robot is behaving perfectly. We saw that the controller contains code for initializing, so using a configuration file we can change how many joints it has or whether it uses position or velocity. And we've seen how it communicates with the system, so we can use different configuration to change out what system is being used to match different robot arms. The next step is to adapt this example to be used for a real robot arm, and we've seen three main changes that we need to do for that. First, the controller is the simplified version, so we don't need that, we can strip it out completely. The second is the robot description file, which we don't need for the controller, but it is useful for being able to do the kinematics, to convert a target tool pose into the joint angles needed to reach that pose. And third, we need to define the entire system for communicating with the robot arm. So we need to define whether it uses serial, whether it uses Bluetooth or something else to send commands to the robot arm and to read back its state values. Between those three things, we can take that example repository and use it for a real robot arm, which is exactly what I'll be doing in a future video. So if you want to watch that, check back here or subscribe to get notifications, and I'll see you there.